Good day and welcome back for the first part of our discussion of triple integrals and cylindrical coordinates. So for this section we're going to continue on with the evaluation and visualization of triple integrals. In fact, we're even going to build up upon the example from the end of the previous video by introducing something called cylindrical coordinates. But the natural starting point for introducing cylindrical coordinates is to just go back to a quick reminder of polar coordinates, which we used extensively with double integrals. And the idea is that if we pick a point in the plane, instead of writing it in these Cartesian, i.e. x comma y coordinates, we're going to represent it as r comma theta, where recall r is representing the distance the point is away from the origin, and theta represents this angle coming up from the positive horizontal axes going in the counterclockwise direction. And remember the standard formulas we introduced relating polar coordinates to Cartesian coordinates. Using some right triangle trig, we have x is equal to r cosine theta, y is equal to r sine theta, and then by the Pythagorean theorem, x squared plus y squared equals r squared. Cylindrical coordinates is going to take this idea of polar coordinates and it's simply going to add a third dimension to it. So we'll think cylindrical coordinates is polar coordinates with a third dimension. And the idea is that any point now in the xyz coordinate plane can be represented as r, theta, z. Where the nice thing is, r and theta still have the same exact significance. If we were to take our point and drop it down into the xy plane, we're going to consider everything in that xy plane in terms of polar coordinates, and z would simply represent the height above the xy plane. And this allows us to very quickly and conveniently write down these relationships once again between Cartesian and cylindrical coordinates. So x would be r cosine theta, and y would be r sine theta, exactly as it was with polar coordinates. And then z is simply equal to z. It is unchanged when we go from Cartesian to cylindrical and vice versa. With the standard kind of restrictions is we want r to be bigger than or equal to 0, and we also want theta typically to be between 0 and 2 pi. And I say for both of these kind of typically in the sense that these are things that we can get around. Remember with polar coordinates, a negative r value would mean that you go in the opposite direction. So it is perfectly reasonable that r could be negative if it needed to be, for an example. And sometimes it is also useful to dip into negative theta values just to have, say, a nice interval to go along with an integral. Similar to the beginning of the semester when we were discussing the three-dimensional coordinate system, it makes sense to pause here for a few minutes and explore several kind of common surfaces in cylindrical coordinates and really see why it is we are interested in this coordinate system. So let's begin by graphing the surface r equals 2 in cylindrical coordinates. So whenever we're talking about cylindrical coordinates, we are thinking three-dimensional space, so implicitly we're asking you to sketch the surface. Now in terms of a set, we want to think of what are all points of the form r theta z, so in cylindrical coordinates, where r is forced to be 2. And recall a perfectly good way to get started is to know what restrictions are not placed. That is to say, theta and z can be anything. And my intuition when I think of theta and z being anything, if theta can be anything, that means every z equals trace of this surface should be circular. Furthermore, if z can be anything, we can go as far down or up that z-axis as we would like. Let's think about this from a very quantitative perspective as well, and if you already have an idea of what this looks like, pause the video for a moment and sketch the surface. From the quantitative perspective, if we start off with r equals 2, the equation in cylindrical coordinates, how can we convert this into Cartesian? And one way to do this is to maybe include a detail up here above that I failed to include. We still have this relationship that x squared plus y squared is r squared. That is to say, if we square both sides, r squared is equal to 4, we would have x squared plus y squared equals 4. And r equals 2 in cylindrical coordinates becomes x squared plus y squared equals 4 in Cartesian coordinates, which is the equation of a cylinder. So we would have a circle of radius 2 in what was formerly that xy plane. So this would be the circle given by r equals 2 if we're thinking polar coordinates. But for cylindrical coordinates, r equals 2 would represent this cylinder. In fact, r equals any positive constant would be a cylinder of that radius around the z-axis. Let's look at one more common surface in cylindrical coordinates. Let's take a similar approach to graph the equation given by z equals r in cylindrical coordinates. And we can reason our way through this using intuition, or we can also work with this equation more quantitatively, which I think is the simplest approach. Note if you start with z equals r, and we once again square both sides, z squared would be r squared, and r squared is x squared plus y squared. And this is a familiar quadric surface that we encountered earlier this semester. It is a cone. So the graph of z equals r would be the cone that we've encountered previously. And note it's really kind of this double cone going both in the positive as well as that negative z direction. And the takeaway from these two examples is that cylindrical coordinates is well suited for describing cylinders and cones. And when we see cylinders and cones coming up as parts of our solid of integration, it may be a reasonable idea to apply cylindrical coordinates. And that will be the starting point for our next video. So stay tuned and take care.